much. Okay. Thank you very much. It's a real pleasure to be able to give this talk here, and thanks to the organizers for inviting me here. So this talk is about quantum reference frames, and it will not be about quantum gravity. So I have actually not even gravity here appears. And quantum reference frames is more like an operational way of quantizing, so of putting reference frames in a quantum state. And this is now a research program, so I will only emphasize some results, and I will totally neglect other results that are, but if you're interested, just come to me and ask me. So the motivation for this is that when we have, if we want to quantize gravity, so if we want to have a quantum description of gravity, then we lose the notion of classical spacetime. And one of the simplest arguments that we can make is that general relativity satisfies Einstein's equations, but the right-hand side of Einstein's equations, we always take it as a classical quantity. But quantum theory tells us that matter is quantum, but we do not know how to plug a quantum stress energy tensor on the right-hand side of Einstein's equations. So what happens to spacetime and when we want to take a quantum stress energy tensor is still an open question in the most general case. And quantum gravity has formulated many arguments, and there are many different approaches that study in which way we should quantize spacetime and the geometry. And here I'm listing just some of them. But now I want to go more basic. So let's forget about the quantum effects of gravity for now, and let's think about what happens if, okay. And let's think if we can talk about a quantum space in some sense, but even without gravity. And the simplest thing we can think of is what happens if I have a quantum system in a quantum superposition state, and I want to center a reference frame on the position of this quantum system. Can I do that? So, as I said, this is a very simple question that does not require gravity, but in the end, the motivation is to build up with a bottom-up approach from this simple setting towards including gravitational effects and possibly quantum gravity, so effects that are not just classical gravitational effects, without going to the Planck scale now. So let us imagine that we have A and C, and this rock would be the center of the reference frame. Now, usually, we always take distances. If we take a relational perspective, the position of C is actually the relative position between C and the center of my reference frame A. And if I want to move the origin of the reference frame from A to C, then I will have the opposite state. I will just put a minus in front of this of the original vector. But now let's consider C in a quantum superposition of two different positions. So now we don't have just one single xc, but we have a quantum operator that describes the position of C from the point of view of A. So we can ask, how does C see A? And more generally, can we attach a reference frame to an object whose state is in a quantum superposition in some basis? So here I'm considering positions. So let me just tell you what, how we describe reference frame transformations in quantum mechanics. So usually, a reference frame is a set of axes with a state of motion. And in quantum mechanics, if I take a particle P and I want to apply a reference frame transformation to that, that will be a unitary operator that, for instance, here I pick two examples, the translation and the boost, where what I would like you to notice is that this x0 is the amount by which I translate, this v is the relative velocity between the initial and the final reference frame, and these are encoded in the transformation as parameters. So they're not dynamical variables, they are not operators. And now, if I want to make one of these transformations, I have to change my state, but I also have to change my Hamiltonian. And in standard non-relativistic quantum mechanics, I say that my transformation law is covariant if in the Hamiltonian that I put after this transformation in the Schrödinger equation changes with this law. In addition, I say that I have a symmetry of the dynamical law if the functional form of the Hamiltonian after the transformation is the same as the functional form of the Hamiltonian before the transformation. But now, let us consider a situation in which initially we stand in C. So we have a reference frame that is centered in C, and we look at two systems A and B. Can we come up with a transformation to move the origin of my reference frame from this yellow rock to this green rock? So something like that, where at this point, A, since we are in a relational picture, A does not describe itself anymore. The state that we describe is actually the relative information from between the reference frame that I'm picking and the external systems. So let's consider the simplest case, that is just translations. Now, initially we stand in C, and we want to achieve this transformation of these coordinate transformations. And if you look at it, this is just vector composition. So let's put our reference frame here. Let's describe a particle B here. And now we just want to move the origin from C to this alpha. So in quantum theory, we just apply this translation operator to the x of B, and this just sends me to x minus A. So I just achieve what I wanted. I just shift the origin from here, and now this position here will be x minus alpha. But now, if instead of having this sharp position, I have something like that, and now I want to shift my position here, I do not know which position to pick. One thing I can do is to take seriously the linearity of quantum mechanics, and I say I do not know which position to pick, but I can pick all of them and just coherently superpose all these different translations. If I do that, I obtain something like of this type. So if you look at it and compare it with this quantity, I had to add one Hilbert space of the quantum reference frame, and I promoted the parameter of the transformation, alpha, to an operator that acts on the Hilbert space of A, the quantum reference frame. This is not quite the end of the story, because I also have to add this other operator that basically we call parity swap operator that has this action. And basically, we need it to realize this line of the transformation. OK, so this is what I just said. Now, let me just give you an example. So once we have this transformation, the state transforms unitarily. This is just a unitary transformation. So in this case, we have A that is in a quantum superposition of two positions of x1 and x2, and B, just for simplicity, in just some fixed position, x0. And now, if I want to do a quantum reference frame transformation to center my origin in A, then what I will do is, if system A is in x1, I will translate B and C by x1. And if system A is in x2, I will translate B and C by x2. And this will be coherently superposed in such a way that this state, that was a product state at the beginning, becomes an entangled state in the final quantum reference frame. And of course, I can just apply then the inverse transformation to go back to my initial situation. So this is a very general feature of quantum reference frames, that is that entanglement and superposition are quantum reference frame dependent. And they're not just properties that are defined a priori. Okay. Now, what happens to the Hamiltonian? Because now I just described what happens at the level of the state, but we also have a Hamiltonian of systems A and B. So that's if we don't have quantum reference frames, we wouldn't have the Hamiltonian of A, but here we're treating them on the same footing. And now I want to translate, I want to change from the initial quantum reference frame of C to the quantum reference frame of A. And I'm just assuming that the quantum reference frame transformation is unitary at this point. I'm not picking a special form. So if I do that, I just basically have to put in the reference frame transformation on the left and on the right. And I will obtain, again, a Schrödinger equation, which means that I have a unitary evolution in the final quantum reference frame. So far, so good. Everything is intuitive. And the Hamiltonian and the state will also transform according to this usual law that we find also in quantum mechanics, and where the system, the only difference is that the reference frame enters as a physical system, as a quantum system in this description. But now, it turns out that we can define a notion that is an extended symmetry transformation in such a way that if we have initially a Hamiltonian of A and B from the perspective of C that depends on mass, position, and momentum of systems A and B, then we can come up with quantum reference frame transformations such that the functional form is the same, but all labels A are swapped to label C. And in particular, we came up with some transformations that are superposition of translations and superposition of Galilean boosts that I do not have time to show you, but we can talk about it later. So these two transformations achieve this. Now, so this general structure of the transformations is basically an operator acting on the Hilbert space of A and B. So it doesn't close a Galilean group because we have made because basically the parameter of the transformation now is an operator, and operators do not commute. But they do close a group. They close a Lie group. And so you can show, and we showed it here, that there is like a group with 7 generators, such that the composition of different elements of this group is just a Lie group. And so you always stay in this. So basically, composing two transformations gives you a transformation that is also allowed. Now, I said that I wanted to connect this with, well, the talks that we had on relational observables. In which way is this a relational framework, and in which way can we show that this is a relational framework? So I already gave you a hint by saying the relative distance and the relative state, but I haven't shown it yet. So what we can do is to come up with so here we have an n-particle model, very simple, just a kinetic term plus interacting Hamiltonian. So it's in one dimension. And in addition, we add a constraint. So this constraint is basically telling us that the total momentum of this n-particle system is 0. So now we want to enforce this constraint. How do we do that? So the long way of which it is done in the paper is just to do it for the classical one and then quantize it in 2 different ways, either with Dirac quantization or reduced quantization. And actually, in this case, they turn out to be the same. Now, let me just show you how we do it in the quantum case. So basically, what we want to achieve is if I have these n particles on the line, I want to pick this red particle and put the origin of my quantum reference frame on this red particle. So if I start from a state, basically the physical, just a general state, the state in the physical Hilbert space are those that satisfy this relation. So basically, all the states that have total momentum equal to 0. Then I can formally write this physical state by doing a group averaging on any state that is defined in the tensor product Hilbert space. And okay, you can show basically, this is basically a representation of the Dirac delta, so roughly it gives you delta P. So it enforces the condition that the total momentum is equal to 0. But then this is not enough yet, because we also have to go to the quantum reference frame of this red particle. And the way we do that is by applying this unitary operator that we call trivialization operator, that is basically a translation on the systems. So in the case we have in the case of 3 particles, this is a translation on the systems B and C by the position of A. This still stays in the space of that solves the constraint, but basically what happens is that you basically put all the redundancy on the Hilbert space of the particle A, and you're left here with this relative state. And then, so of course we know that we have to redefine the inner product when we do this procedure, and we do that by basically removing this state with by projecting on this operator. That incidentally, notice that this is the projection over the state xa equal to 0. So basically, roughly, what happens is that here we have a constraint that induces a gauge freedom, and then we fix the gauge redundancy, and this would be the projection over the classical gauge condition. Now, we can do this for 2 different particles. And so imagine we have this n particles model. We do it for particle A and for particle C. And then we want to go from one to the other without going back to this general perspective neutral structure. So basically to the level of where we impose the constraint. If we do it from reduced Hilbert space to reduced Hilbert space, we find exactly the transformation that I defined to you earlier with an intuitive procedure. Now, what does this have to do with relational observables? Well, because it turns out that the relative distances between the particles are the Dirac observables. So, now, this is for what concerns space. But this whole mechanism for quantum reference frame was developed having in mind space-time. Let me just add, now, again, I will consider a very simple setting, because I only want, so I still want to talk about particles, but let me add also the time direction in space-time. And the way I'm going to show this to you is to have, again, a set of n particles which have additional internal degrees of freedom that we use as clocks. And in addition, basically, I want to encode the dynamics of the particles by using a constraint, a dynamical constraint. And this is something that, okay, I forgot to put the references here, but so this is called covariant quantum mechanics. It has been developed among other people in the 90s by like Michael Reisenberger, Carlo Rovelli, Halliwell, and collaborators. So it is, that's something that I didn't make up, it exists. But basically the idea is that you introduce a redundancy in your description of the dynamics, and then you enforce the constraint to remove this redundancy. And if you notice here, so here we have a G00, and if the G00, if we just have a Newtonian, basically a Newtonian gravitational field, once you enforce this constraint, you recover the usual kinetic term plus Newton potential. So it's really nothing very strange. In addition to that, so this was our constraint of the last slide, the total momentum. But we also add an additional constraint here that is basically constraining the total energy of this particle. That is the P0, so basically the P0 of the particle, plus the internal energy of the clock in an arbitrary reference frame. So this is basically a time dilation factor. And the internal energy of the clock is the energy of its internal degrees of freedom, so the HI. So now this is, OK, so this is basically an extension of, for those of you who are familiar with it, the Page and Wooter's approach. Because here we have P0s in addition to that, and this time dilation factor. Well, in the Page and Wooter's, you also only have the Hamiltonian, the sum over all the internal Hamiltonians of the clocks. And this is what I showed you in the previous slide. So basically, we can think of this as a conservation of, well, in this case, the 2 momentum, because it's in 1 plus 1, but say for momentum. So basically, now we can do the same, a very similar reduction procedure to the perspective of one of these particles. And what we obtain is a Schrödinger equation in the proper time of each clock that composes our system of clocks. And what you obtain is some external Hamiltonian of these clocks. And interestingly, here we have the gravitational time dilation factor that we would expect from classical physics, but just in a quantum superposition, because these clocks are in a quantum superposition. And OK, so basically, this is the explicit form of the time dilation factor for each clock, where basically this is the jth clock minus the source, basically the position of the source of the gravitational potential, minus basically the position of the gravitational potential from the perspective of the clock that we are picking as our quantum reference frame. So what happens if now the source of our gravitational potential is the Earth? What happens is that, for instance, we can have a situation in which we have an A clock and the B clock. So A would be at a fixed height from the center of the Earth, and the B clock is in a quantum superposition of 2 different trajectories. And what we obtain here, I don't have time to show it more like with equations, but intuitively, what happens here is that when A looks at the time that B is measuring, B's time is in a quantum superposition of times from the perspective of A. But vice versa, if I go to the quantum reference frame centered on clock B, A runs in a quantum superposition of times from the perspective of B. Instead, if I now put A and B in an entangled state where they always go in the same path in the interferometer, what I see is that if I go to the quantum reference frame of one of the 2 clocks, the other one always agrees with the clock that I'm choosing. So this is basically the end of my talk. To wrap up, I introduced a formalism for quantum reference frames. That means we associate a reference frame to a quantum system that can be in any arbitrary quantum state. And this is motivated by the fact that we have to promote space and time to in some quantum way when quantum systems serve as a reference frame, in light of the fact that in the end we want to put gravity inside this formalism. And this is basically the next step. So what we need to do now is, so this is still pretty recent work, so we are working our way up, and we had the first results now where we have also some gravitational aspects included in this. But now we really have to modify it and extend this framework to include gravity explicitly in it. And I would say that the relation to non-classical spacetime is still unknown. So for instance, what happens if I change the quantum reference frame when I have a mass in a quantum superposition and I want to go into this mass, into the reference frame of this mass, what is the description of the gravitational field from the perspective of different quantum reference frames? What is the structure of reference frame transformations? What are the properties of non-classical spacetime and how do they vary when I change quantum reference frame? What are the observable features that possibly we could even test in experiments that are now trying to realize a quantum superposition of massive objects? And yeah, so, and do we gain anything with this quantum reference frame perspective? So these are all questions that I'm going to address in the future in my next research. And with this, I would like to thank you for your attention.
Thank you. Right on time. No fluctuations. First question.
Just a simple question. I'm not an expert in the field, but I would like to understand why you have used, for example, the Schrödinger equation and not the Dirac equation, because this is relativistic.
Good. Yeah, so this was just the start. So the beginning of this program was to really just simplify technically as much as possible what we were doing, to identify already at the level of quantum mechanics where the conceptual problems were. And this, we expect them to carry over also to quantum field theory, possibly becoming words. And now, so we have done we have realized a quantum reference frame as one particle sector of a Dirac particle, in particular a particle with spin 1/2. And there, okay, so the technical aspect is we use the Foldy-Wuthuysen representation of the field to decouple the motion of the spin from the external degrees of freedom. And we have used that, for instance, to find an operational way of defining a covariant spin operator. So we defined the relativistic Stern-Gerlach experiment, and that was more motivated from quantum information. There is some work from Daniel, who is here in the audience, where they prove that if you just use the spin, like your usual definition of spin in a relativistic context, then you get decoherence. And then if you want to encode instead quantum information in the spin degree of freedom for a fast-moving particle, close, say, relativistic particle, then you have to change your spin operator. And so we found an operational way of setting that problem up so that you can have basically a qubit encoding of quantum information in this particle.
There's another question up there. Why is there?
So thank you for the talk. So I just have questions. Maybe it's naive, but it's purely quantum. Maybe you can we apply this relative reference frame is already discovered in quantum in atom physics, that there's the Zeeman effect, like we change the the frames into the atom and we see the nucleus spinning around the electron. So maybe we can we use this formalism and to have an equivalent description of the Zeeman effect, or there's another effect that is called the Bohm-Aharonov.
Yeah.
So there's an electron moving through a magnetic coil, and then after that it's experienced some change in phase. So maybe we can also apply this into the perspective of the moving electron and see like if we can get some novel description of the two.
No. So that's a good question. So the reason why we have not seen any of these effects in experiments so far is that we can always approximate the trajectory of particles as semi-classical trajectories, basically. And so the width, the quantum width of the state is always negligible, and at most is in a quantum superposition of semi-classical trajectories. So we don't observe these. But it's true, in principle, we could do something like that. And that's, so I'm also discussing the possibility of setting up such an experiment with experimentalists like Marcusa Spellmeier. So yeah, and so experiments that prove this type of effects are definitely one of the important things that have to be thought about.
Thank you.
Okay, so we have to stop here for now with questions. There will be another discussion period. So thank you again first.